In the profound stillness between stars, in the quiet drift of cosmic dust across light years, you are here. Right now, as these words reach you, you are sitting inside a galaxy, an island universe of stars and mysteries, a spiral of ancient light stretching 100,000 light-years from its far-flung edge to the other. To the human experience, born of horizons measured in miles and landscapes scaled to our stride, this number is an abstraction of paralyzing grandeur. 100,000 light-years. It means that light itself, the fastest entity in existence, traveling at 670 million miles per hour, would require 100 millennia to make that solitary crossing. It means that a beam of light leaving one galactic rim when our species first mastered fire would only now, at this moment of our technological adolescence, be arriving at the opposite shore. Within this vast arena, every human story has been written. Every joy, every sorrow, every triumph and failure of our kind has unfolded beneath the silent arch of this galactic cathedral. And yet, this magnificent expanse, this stage for all of human history, is not merely dwarfed by the true scale of the cosmos. It is utterly, humiliatingly insignificant. In the year 2022, astronomers gazing into the deep fields of the constellation Lynx found something that should not exist. A galaxy so colossally vast that light would require not thousands, not hundreds of thousands, but 16 million years to journey from one end to the other. 16 million years. A span of time in which entire species evolve, continents reshape themselves, and civilizations rise and fall into dust, all within the mere traversal of a single structure. Our entire Milky Way, with its 400 billion stars, could be placed inside this cosmic titan not once, not 10 times, but more than 160 times over, with room to spare. This entity, named Alcyoneus, redefined the very meaning of galaxy. But the universe, in its relentless creativity, is not content with a single definition of immensity. For Alcyoneus, though the largest known structure of galactic origin is not the heaviest, that distinction belongs to another Leviathan, catalogued as IC 1101. Residing at the heart of a distant galaxy cluster, this elliptical behemoth does not stretch with delicate plasma wings, but instead concentrates sheer, staggering mass. It contains an estimated 60 trillion to 100 trillion stars. To comprehend this number is to confront the failure of human intuition. Our Milky Way's 400 billion stars are but a fleeting breath against the hurricane of this galactic giant. IC 1101 holds within its gravitational embrace 40 to 80 times more stars than every galaxy in our entire local neighborhood combined, more stellar furnaces than exist in the Milky Way, Andromeda, the Triangulum galaxy, and all their dozens of satellite dwarfs, multiplied many times over. These are not mere statistical curiosities. They are existential signposts. The discovery of such monsters forces upon us a series of profound and unsettling questions. Have we stumbled upon the upper limits of cosmic architecture? Or do these giants merely hint at structures yet more unimaginable, lurking in the unexplored darkness? What fundamental laws of physics permit, or perhaps even demand, such extremes? And what does our own pale blue dot, orbiting an ordinary star in an ordinary galaxy, signify in a universe capable of such boundless, terrifying grandeur? The story of these galactic titans is more than an astronomical catalogue. It is a narrative of scale, a meditation on limits, and a humbling lesson in our place within the cosmic tapestry. To understand them is to begin to understand the universe's true nature, a nature that is far stranger, far more vast, and far more wondrous than we ever dreamed. Our galaxy feels infinite. On a clear, dark night, far from the polluting glow of human habitation, the Milky Way arches across the heavens like a river of crushed diamond and myth. To the unaided eye, it is a haze, a luminous path, woven from the combined radiance of countless unresolved stars. For millennia, this band of light was the totality of the known universe. Ancient astronomers saw in it the seam of the celestial sphere, the spilled milk of divine legends, the backbone of the night. They traced constellations along its length, crafting stories of heroes and monsters, projecting human drama onto the immutable stars. They believed, with a certainty born of limited perspective, that this was all there was, that the Earth sat motionless at the center of creation, with the fixed stars embedded in a perfect crystalline sphere just beyond the wanderings of the planets. This geocentric illusion was persistent, comforting, and profoundly wrong. The first crack in this cosmic egg appeared not with a grand theory, but with a simple instrument pointed toward the heavens. In 1609, Galileo Galilei turned his primitive telescope, a tube with lenses of ground glass, toward that milky band. What he saw shattered the classical cosmos. Where the naked eye saw a smooth, ethereal glow, Galileo's lens resolved a countless multitude of individual stars, far more than anyone had imagined. He saw mountains on the moon, spots on the sun, and moons orbiting Jupiter, a solar system in miniature that defied the Earth's unique centrality. But even Galileo could not fathom the true scale of what he was glimpsing. The Milky Way, he presumed, was simply the realm of the stars, perhaps extending a few thousand times the distance to Saturn. The idea that those faint, fuzzy patches of light, he also observed, the nebulae, were themselves distant, island universes, comparable to our own star system, was a heresy beyond even his revolutionary imagination. The true nature of our galaxy and its place in the cosmos required centuries of patient measurement, theoretical leaps, and technological innovation. The crucial breakthrough came in the early 20th century, with the work of astronomers like Harlow Shapley and, most famously, Edwin Hubble. Shapley, by mapping the distribution of globular clusters, dense spherical swarms of ancient stars, deduced that the Sun did not reside at the center of the Milky Way, but was instead stationed in its distant suburbs, roughly 25,000 light-years from the galactic core. This was a profound emotion, a Copernican revolution on a galactic scale. Our star was not special, our position not central. Then Edwin Hubble delivered the coup de grace. Using the powerful new Hooker telescope at Mount Wilson Observatory, he studied the Andromeda Nebula. Within it, he identified a class of variable stars called Cepheids, whose pulsation periods are directly linked to their intrinsic brightness. By comparing their apparent dimness to their known true brightness, he could calculate their distance. The result was staggering. Andromeda was nearly 1 million light-years away, far beyond the then estimated bounds of the Milky Way. That faint smudge was not a cloud of gas within our galaxy, but an entirely separate galaxy, a colossal island of stars in its own right. In an instant, the universe expanded by a factor of thousands. The Milky Way was not the universe. It was one galaxy among countless others. With this new perspective, we could finally begin to take the measure of our galactic home. We now understand the Milky Way as a barred spiral galaxy, a vast rotating disk of stars, gas and dust, shaped like a colossal pinwheel with a central bar-like structure. Its disk, where our solar system resides, is about 1,000 light-years thick and 100,000 light-years across. Embedded within it are magnificent spiral arms, waves of density where gas is compressed, triggering the birth of brilliant short-lived stars that trace out the galaxy's architecture in blue-white light. At the very center lies a supermassive black hole named Sagittarius A*, with a mass equivalent to 4 million suns, a silent gravitational anchor around which the galaxy slowly turns. Our galaxy is home to an estimated 200 to 400 billion stars. Each is a sun, a nuclear furnace fusing hydrogen into helium and, in their final stages, creating the heavier elements that make up planets and life. Between these stars lies the interstellar medium, a diffuse mixture of gas, primarily hydrogen and dust grains of silicon and carbon. This is the raw material for future generations of stars. The galaxy also contains a vast spherical halo of ancient stars and globular clusters, as well as an immense invisible shroud of dark matter, whose gravitational pull is the unseen hand that governs the rotation of the galaxy itself. From our vantage point within the Orion Arm, the Milky Way is the entirety of our cosmic experience, the canvas upon which every human life has been painted. And yet, for all its splendor and complexity, the Milky Way is, by the cold metrics of cosmic demographics, utterly ordinary. Of the 2 trillion galaxies estimated to populate the observable universe, the Milky Way is a mid-sized specimen, unremarkable in mass, luminosity, and morphology. Its central black hole is modest by the standards of elliptical galaxy behemoths. Its star formation rate is average. It is a typical spiral galaxy in a typical group of galaxies. This very ordinariness, however, is what makes the discovery of the true cosmic titans so jarring. If our galaxy is a standard brick in the cosmic edifice, then entities like Alcyoneus and IC 1101 are the grand arches, the soaring vaults, the foundations of mountains. They reveal that the universe's architectural plans include blueprints for structures that defy our standard models and strain our capacity for wonder. The story of these giants begins not with a fanfare, but with the patient accumulation of data, the subtle anomaly in a radio map, the faint, extended glow on a photographic plate that refused to conform to expectation. Their discovery timelines are as vast as the structures themselves, stretching across decades of astronomical history. IC 1101, for instance, was first noted in 1895 by the astronomer John Louis-Émile Dreyer and included in his index catalogue, hence the designation IC. For generations, it was considered just another nebula, a fuzzy patch of light, presumably within our own galaxy. Its true nature remained hidden by its immense distance and the limitations of early telescopes. Only with Hubble's revelation of the extragalactic universe did IC 1101 slowly begin to give up its secrets, transforming from a curious nebula into a suspected galactic monster at the heart of the distant Abell 2029 cluster. Alcyoneus's story is even more recent. and hinges on a different kind of vision. It is not a galaxy that reveals its full glory to optical telescopes. Its immensity is written in wavelengths invisible to the human eye, the long, slow waves of radio light. The discovery was made in 2022 by a team led by astronomer Martijn Oey at the Leiden Observatory, using data from the low-frequency array LOFAR, a revolutionary radio telescope network spread across Europe. LOFAR's thousands of small antennas combine to form a virtual eye of unprecedented sensitivity to faint, low-frequency radio emissions. When Oey and his colleagues processed the data from a survey of the sky, they found a pair of colossal radio lobes emanating from a seemingly ordinary galaxy 3 billion light-years away. The lobes were so vast that the team initially dismissed them as artifacts, errors in the data processing pipeline. Only after painstaking verification, rechecking calibrations, reprocessing with different algorithms, comparing against all known sources of interference, did the incredible truth emerge. The structure was real. They had found a radio galaxy spanning 16.3 million light-years, shattering the previous record by a factor of 5. These two discoveries, separated by over a century and employing completely different astronomical techniques, point toward the same profound conclusion: our understanding of cosmic scale was hopelessly parochial. The universe builds on a loom whose frame is larger than we had dared to imagine. But to truly grasp what these numbers mean, we must move beyond mere figures and attempt to contextualize them, to feel the weight of these scales in a human sense. This is a formidable challenge, for our brains did not evolve to comprehend the cosmic. We are products of a world where distances are measured in steps, time in seasons, and quantities in handfuls. Our intuitive number sense fails catastrophically beyond a few thousand. So we must build bridges of analogy, though we know they will be fragile indeed. Consider time. Light travels at 186,282 miles per second. In 1 year, it covers nearly 6 trillion miles, a distance we call a light year. Now envision a photon of light beginning a journey across Alcyonius from one tip of its radio lobe to the other. As that photon embarks, here on Earth, the ancestors of humanity are diverging from the lineage of chimpanzees. The first stone tools have not yet been fashioned. As the photon crosses the first million light-years, Homo habilis emerges in Africa, taking the first tentative steps toward technology. At the halfway point, 8 million years into its journey, Homo erectus has mastered fire and begun to migrate out of Africa. As the photon enters the final million light-year stretch, Homo sapiens paints the caves of Lascaux, invents agriculture, builds the pyramids, writes philosophy, discovers electricity, and launches probes beyond the solar system. The photon completes its crossing now, at this very moment arriving at our telescopes, having witnessed the entire saga of human evolution as a brief, flickering instant in its multi-million-year voyage. All of that time, all of that history, is contained within the simple traversal of a single celestial structure. Now consider number. The Milky Way's 400 billion stars. To count them at a rate of 1 per second, without pause for sleep, food, or breath, would take you over 12,700 years. You would have to have started counting before the dawn of agriculture, and you would finish to task. That task feels impossibly long, a futile effort spanning the entirety of civilization. Now attempt the same for IC 1101, with a conservative estimate of 60 trillion stars. Counting one per second would require approximately 1.9 million years. You would begin counting before Homo sapiens existed, counting through the rise and fall of ice ages, the migration of our ancestors across continents, the birth of language, the construction of cities, the entire pageant of human history, and you would still be counting, with tens of thousands of generations yet to come. The scale is not additive, it is exponential. It exists in a different conceptual dimension. The sheer physical space these galaxies occupy also defies terrestrial analogy. If our solar system, out to the orbit of Neptune, were shrunk to the size of a coffee cup, the Milky Way on that scale would be roughly the size of the continental United States. On that same scale, Alcyoneus would stretch from the Earth to the Moon. IC 1101, though not as long as Alcyoneus, would be a massive, bloated sphere, perhaps the size of the Sun itself relative to our coffee cup solar system. These are not just bigger objects. They are orders of magnitude that reshape the very coordinate system of reality. What could possibly create such monsters? The answer lies in the two divergent paths to cosmic enormity that these galaxies represent. IC 1101 is a product of gluttony, of gravitational accumulation on a scale so relentless it borders on the obscene. Alcyoneus is a product of power, of focused energy projection that carves its signature across intergalactic space for millions of years. They are the ultimate expressions of two fundamental forces, gravity and electromagnetism, channeled through the most extreme engines the universe provides. IC 1101 resides at the dynamical heart of the Abell 2029 galaxy cluster, a vast metropolis of hundreds of galaxies bound together by gravity. In such dense environments, the central region acts as a deep gravitational well, a cosmic pit into which material inevitably falls. For billions of years, IC 1101 has sat at the bottom of this well, acting as a voracious predator. Its growth has been fueled by galactic cannibalism. Smaller galaxies, drawn in by its immense gravity, have spiraled inward and merged with the central giant. Each merger is not a collision in the sense of stars crashing. The distances between stars are far too vast for that, but a slow gravitational dance that scrambles orbits, funnels gas toward the center, and ultimately erases the identity of the smaller galaxy, assimilating its stars into the swelling halo of the giant. Imagine a history written in violence. Over the course of perhaps 12 billion years, IC 1101 has consumed hundreds, possibly thousands, of other galaxies. Some were small dwarf galaxies, mere snacks. Others were substantial spirals like our own Milky Way, major meals that added billions of stars at a time. With each merger, the central black hole itself, the product of the merger of the progenitor black holes, grew larger, its gravitational grip tightening, making the galaxy an even more effective trap. The galaxy grew fatter and rounder, its orderly spiral structure erased by the chaotic, random orbits imparted by countless mergers, transforming it into the featureless, golden-hued elliptical behemoth we see today. Its reddish color is the telltale sign of age. The hot, blue, short-lived stars have long since died, leaving behind a population of ancient cooler red giants and dwarfs. IC 1101 is a cosmic retirement home, a gilded necropolis of stars, most of which were born in the universe's exuberant youth. At its heart lies the engine of its past gluttony, a supermassive black hole of almost incomprehensible mass. Estimates range from 40 to 100 billion times the mass of our Sun. To grasp this, consider that our galaxy's central black hole, Sagittarius A*, is a mere 4 million solar masses. The event horizon, the point of no return of IC 1101's black hole, would, if placed in our solar system, extend far beyond the orbit of Pluto, swallowing the entire planetary system whole. This black hole is currently quiet, dormant, having exhausted the readily available fuel in its immediate vicinity. But its silent presence is the gravitational anchor around which this city of stars revolves, a monument to the countless galactic feasts of the past. Alcyonius, in stark contrast, is not about mass accumulation, but about energy expenditure. Its host galaxy is unremarkable, a fairly standard galaxy with a central black hole of perhaps 400 million solar masses, large but not extraordinary. What makes Alcyonius a record holder is not the galaxy itself, but what emanates from it. Two colossal jets of relativistic particles inflating enormous lobes of magnetized plasma that stretch 8 million light-years in opposite directions. This is a radio galaxy, a specific and spectacular class of active galaxy. The process begins with the supermassive black hole at the galaxy's core. When gas, dust, or even entire stars fall toward this gravitational abyss, they don't plunge straight in. Instead, they form a swirling, superheated accretion disk, a maelstrom of plasma moving at near light speed. Intense magnetic fields, twisted by the disk's furious rotation, act like cosmic railguns, channeling a portion of this infalling material into two narrow, oppositely directed jets that blast outward at velocities approaching light itself. These jets are composed of electrons, positrons, and other particles, accelerated to energies that dwarf anything produced in human particle colliders. For millions of years, these jets have been punching into the intergalactic medium, the thin, diffuse gas that fills the space between galaxies. As they plow forward, they inflate vast, balloon-like cavities of hot, magnetized plasma, the radio lobes. The particles within these lobes spiral around magnetic field lines, emitting synchrotron radiation, which we detect as radio waves. What makes Alcyonius special is the extraordinary length these jets have achieved. Most radio galaxy jets dissipate their energy after a few 100,000 or a few million light-years. Alcyonius's jets have propagated over 16 million light-years in total, creating the largest single structure of galactic origin ever identified. Why did Alcyonius grow so large? The leading hypothesis points to its environment. It appears to reside in a region of space that is unusually empty, a cosmic void or underdense filament. In this sparse neighborhood, the jets encounter less resistance from the intergalactic medium. With fewer atoms to bump into, they can maintain their focus and momentum for far longer, inflating lobes to unprecedented sizes before finally dissipating their energy. It is a cosmic coincidence of location, an active galaxy with powerful jets placed in the emptiest of parking lots, allowing its outburst to expand almost unimpeded. The discovery of these giants forces astrophysicists to confront the limits of their theories. Computer simulations of galaxy formation and cluster evolution can produce massive central galaxies, but ones as extreme as IC11. One push at the upper boundaries of what the models predict. Similarly, theories of jet propagation and radio lobe growth suggested a maximum size far smaller than Alcyoneus. These galaxies are not just big, they are too big, challenging us to refine our understanding of feedback mechanisms, gas cooling, dark matter, halo growth, and jet physics. They are natural experiments conducted on a galactic scale, revealing the parameters of cosmic physics under the most extreme conditions. Beyond the astrophysics, these entities stir deeper, more philosophical questions about life and perspective. Imagine for a moment a planet orbiting a star in the outer halo of IC1101. The night sky there would be utterly alien. Instead of the familiar, sparse scattering of a few thousand stars visible from Earth, the sky would be ablaze. Toward the galactic center, the heavens would glow with a continuous, diffuse light from tens of billions of unresolved stars, a perpetual dull twilight. Countless stars would be bright enough to cast shadows. The concept of darkness would be different. True black might only be found looking directly away from the galactic bulge. Satellite galaxies, torn remnants of past mergers, would litter the sky as prominent smudges. The sense of being in a crowded ancient metropolis would be inescapable. Conversely, consider a world somehow existing within the radio lobes of Alcyoneus. The structure itself would be invisible to human eyes, a ghost of magnetized plasma. But the environment would be permeated by intense magnetic fields and low-level synchrotron radiation. Auroras might dance across entire hemispheres, triggered not by a solar wind, but by the ambient particle bath of the lobe. The central galaxy would be a distant, insignificant speck, millions of light-years away. The dominant feature of the cosmos for such a civilization would be the immense invisible energy field in which they were embedded, a fundamentally different cosmic experience. The existence of such giants also expands the possibility of life in the universe. Statistically speaking, if the development of intelligence is an improbable but non-zero phenomenon per stellar system, then a galaxy with 60 trillion stars presents a staggering multiplication of chances. IC1101 could harbor millions of civilizations, utterly unaware of one another, separated by gulfs of space and time that make interstellar communication as daunting as it is for us. Each would have its own cosmic narrative, its own astronomy, its own philosophy born from its unique vantage point within the golden hive of stars. Ultimately, the story of Alcyoneus and IC1101 is a story of cosmic humility and wonder. They show us that the universe is not merely larger than we imagine, but larger than we can imagine. Our Milky Way, the canvas of our entire history, is a speck. Our planet, a pale blue dot orbiting a mediocre star in a quiet suburb of that speck, is less than a microscopic grain of sand on the shore of a cosmic ocean whose vastness numbs the mind. Every human conflict, every grand empire, every personal triumph and tragedy has occurred on that infinitesimal grain. And yet, there is a profound counterpoint to this humility. It is from this grain of sand that we have looked out and seen these giants. We have built instruments that capture radio waves from 3 billion light-years away. We have devised theories of gravity and relativity that allow us to understand the physics of black holes and galactic evolution. We have mapped the large-scale structure of the universe. The very consciousness that feels dwarfed by this scale is also the consciousness that conceived the mathematics and built the technology to measure it. In a universe seemingly indifferent to life, matter has arranged itself into complex patterns that can contemplate the whole. The discovery of the biggest galaxies ever found is more than a scientific milestone. It is a mirror held up to our species. It shows us our physical insignificance with brutal clarity. But it also reveals the staggering reach of our curiosity and intellect. We are the universe becoming aware of itself, and in learning about these colossi, we are taking the first tentative steps toward understanding the full scope of our home. The journey has just begun. The darkness beyond our galactic shore holds mysteries and structures that will, no doubt, continue to shatter our conceptions, pushing the boundaries of the possible ever outward into the infinite night. We must now delve deeper into the specific nature of each titan, to understand not just their scale, but their anatomy, their history, and their ultimate fate. We begin with the heavyweight champion of stars, the devourer of galaxies, the ancient monarch at the heart of the cluster. Residing approximately 1.045 billion light-years from Earth in the constellation Virgo, IC 1101 is not merely a large galaxy, it is the quintessential example of a CD galaxy, a giant diffuse galaxy that dominates the center of a rich cluster. Its location is key to its existence. The Abell 2029 cluster is a massive gravitational aggregation of matter, and at the bottom of its potential well, where the gravitational pull is strongest, sits IC 1101, growing fat on the constant inflow of cosmic debris. Measuring its size is a lesson in astronomical nuance. Galaxies do not have sharp edges. They fade gradually into the intergalactic void. Where does a galaxy truly end? Is it at the limit of its visible starlight? The extent of its neutral hydrogen gas? The boundary of its dark matter halo? Each definition yields a different answer. In optical light, tracing the distribution of stars, IC 1101 spans a mind-boggling 4 to 6 million light-years in diameter. Some studies of its faint outer envelope suggest it could even be larger. Compare this to the Milky Way's 100,000 light-year disk. IC 1101 is 40 to 60 times wider. If placed in its center, our entire galaxy would be a mere satellite, a speck in its overwhelming glow. But physical extent is only one measure of its dominance. Its stellar mass is the true record breaker. Estimates, derived from measuring its luminosity and the colors of its stars, suggest it contains between 60 and 100 trillion solar masses worth of stars. The uncertainty itself, 40 trillion solar masses, is larger than the total stellar mass of our local group of galaxies. To put this in perspective, if the Milky Way's stars were represented by a single grain of sand, IC 1101 stars would fill a large dump truck. This is not a difference of degree, but of kind. The light from this galaxy tells a story of great age. Its color is a uniform, warm, reddish yellow. In astronomy, color is a direct indicator of stellar population. Blue light comes from massive, hot, young stars that burn furiously and die young in supernova explosions. Red light comes from older, cooler stars like red giants and dwarfs. The pervasive red glow of IC 1101 means its era of vigorous star formation is long over. It peaked, perhaps 10 billion years ago, when the universe was a quarter of its current age. Most of its stars were born in that frenzied early epoch, and they have been quietly burning through their nuclear fuel ever since. The galaxy is a stellar graveyard, slowly being illuminated by the dimming embers of countless ancient suns. How did it get so big? The process is one of hierarchical merging, the standard model of galaxy growth, but taken to its ultimate extreme. In the early universe, small protogalaxies formed in the densest knots of the cosmic web of dark matter. Gravity drew them together. Collisions and mergers began. In the crowded environment of what would become the Abell 2029 cluster, these mergers happened with relentless frequency. The largest galaxy in the region, the progenitor of IC 1101, had a head start. Its slightly larger mass gave it a slightly stronger gravitational pull, allowing it to capture and absorb its nearest neighbors more efficiently. This process is a positive feedback loop. The more you eat, the bigger you get. The bigger you get, the more you can eat. Over billions of years, this central galaxy acted as a galactic Pac-Man, moving through the crowded cluster center and consuming everything in its path. The mergers were not gentle. When two galaxies merge, their gravitational fields interact violently. Tidal forces rip stars from their original orbits, scattering them into vast, diffuse halos. Gas clouds collide, shock, and compress, triggering brief, intense bursts of new star formation, a final fireworks display before being quenched. The ordered rotational motion of spiral disks is completely destroyed, replaced by the random, chaotic orbits that characterize elliptical galaxies. Each merger adds not just stars, but also the supermassive black holes at the galaxy's centers. These black holes eventually spiral together and merge in a cataclysmic event that shakes the fabric of space-time, emitting gravitational waves. The black hole at the heart of IC 1101 is the product of thousands of such mergers, a Frankenstein's monster of singularities. Evidence of this violent history is etched into the galaxy itself. Although it appears smooth and featureless in small telescopes, deep, sensitive images reveal subtle structures, faint shells, ripples, and tidal streams of stars. These are the gravitational echoes of past mergers, like ripples on a pond after stones have been thrown in. Stars from devoured galaxies are not instantly homogenized. They retain for billions of years coherent structures that trace their tragic origins. Furthermore, detailed spectroscopic studies can reveal distinct populations of stars with different chemical compositions. Some born in the original core of IC 1101, others with the chemical fingerprints of alien galaxies now forever assimilated. The environment of Abell 2029 is itself a testament to IC 1101's dominance. The space between the cluster's galaxies is not empty. It is filled with a tenuous but incredibly hot plasma known as the intra-cluster medium, heated to tens of millions of degrees by the gravitational energy of the cluster's formation. This gas glows brightly in X-rays, outlining the cluster's shape. IC 1101 sits at the very peak of this X-ray emission, like a spider at the center of a web. The galaxy has gravitationally captured vast quantities of this hot gas, but the gas is so energetic it cannot cool and condense to form new stars. It simply sits there, a massive, invisible halo of searing plasma, adding to the galaxy's total mass, but not to its light. This brings us to the true totality of IC 1101's mass, which includes the immense, invisible shroud of dark matter. Through the phenomenon of gravitational lensing, where the galaxy's gravity bends and distorts the light from even more distant galaxies behind it, astronomers can map its total gravitational field. The results are staggering. The dark matter halo of IC 1101 likely extends for tens of millions of light-years, encompassing the entire inner region of the Abell 2029 cluster. The ratio of dark matter to visible matter might be as high as 100 to 1. This means the total mass of the IC 1101 system, stars, gas, dark matter, could be well over a quadrillion, 10 circumflex, 15 solar masses. It is a gravitational empire whose influence stretches across a significant fraction of the cluster. What is the future for this galactic monarch? Its growth, though slowing, is not over. Smaller galaxies still orbit it, and over the next tens of billions of years, many will spiral in and be consumed. But the universe is changing. Dark energy, the mysterious force causing the accelerated expansion of the cosmos, is beginning to dominate on the largest scales. Over time, this acceleration will isolate galaxy clusters from one another. Within the Abell 2029 cluster itself, gravity will remain supreme, so mergers will continue until there is essentially nothing left to merge with. IC 1101 will eventually absorb most of its remaining satellites, becoming a solitary, ultramassive elliptical in an otherwise empty cluster core. Then, over even longer timescales, stellar evolution will take its course. The remaining stars will burn out. The massive ones will have long since exploded or collapsed into black holes and neutron stars. The lower mass stars, like red dwarfs, will continue to glow for trillions of years, but eventually even they will exhaust their fuel. The galaxy will dim, becoming a ghostly swarm of stellar remnants, white dwarfs cooling to black, neutron stars and black holes, all orbiting the central supermassive black hole. That black hole, now truly alone, will endure for timescales that make the current age of the universe seem like a blink. It will slowly evaporate via Hawking radiation, a process so slow that it would take a number of years, written with over 90 zeros, to complete. IC 1101 will end its days not with a bang, but with the slow, cold whisper of quantum physics in an ever-expanding, darkening void. From the devourer of worlds, we turn to the cosmic beacon, the structure of pure energy, Alcyoneus. Its story is not one of accumulation, but of eruption, not of gravity's slow pull, but of magnetism's fierce push. Discovered in 2022, Alcyoneus immediately challenged our understanding of how large a single astrophysical system could become. Located a staggering 3 billion light-years away in the direction of the constellation Lynx, Alcyoneus is a radio galaxy. Its immensity is not in stars, but in the vast lobes of plasma that stretch away from its host galaxy. The host itself, when viewed in optical light, is unremarkable. A galaxy with perhaps a few 100 billion stars harboring a supermassive black hole of roughly 400 million solar masses. Nothing in its visible appearance would hint at its extraordinary nature. Its secret is written in radio waves. The discovery was made using the Low-Frequency Array (LOFAR), a revolutionary telescope designed to detect long-wavelength radio emissions. LOFAR's design is unlike traditional dish telescopes. It consists of thousands of simple dipole antennas spread across Europe, whose signals are combined digitally to create a single, highly sensitive virtual telescope. This makes it exceptionally good at detecting large, faint, diffuse structures, precisely the kind that make up the lobes of radio galaxies. When the team processed data from the LOFAR 2-meter sky survey (LOTSE), they found a pair of enormous bubble-like structures symmetrically placed on either side of a distant galaxy. Careful analysis ruled out instrumental artifacts or chance alignments. The lobes were real and associated with the galaxy. The measurement of their angular size on the sky, combined with the known distance to the host galaxy, yielded the breathtaking physical size, a total span of 16.3 million light-years, with each lobe about 8 million light-years long. This dwarfed the previous record holder, a galaxy known as J1420545, which spans about 5.5 million light-years. To understand Alcyoneus, we must delve into the violent physics of active galactic nuclei. At the core of the host galaxy, the supermassive black hole is not dormant. It is actively feeding. Matter, gas, dust, maybe even entire stars, is spiraling into the black hole's gravitational grip, forming an accretion disk. This disk is a maelstrom of friction and magnetic fields, heated to millions of degrees, glowing brightly across the electromagnetic spectrum. But not all the infalling matter crosses the event horizon. A significant fraction, perhaps fueled by the immense rotational energy of the black hole and the twisted magnetic fields anchored in the disk, is magnetically catapulted away from the poles at relativistic speeds. This creates two oppositely directed, tightly collimated jets. These jets are not solid beams, but flows of plasma, a soup of electrons, positrons, and atomic nuclei, all accelerated to nearly the speed of light. As they blast out of the galactic core, they punch through the galaxy's own interstellar medium and then into the even more tenuous intergalactic medium. For millions of years, these jets have been plowing forward. The material at the head of the jet builds up like snow in front of a plow, creating a working surface where the jet's energy is transferred to the surrounding gas. This inflates gigantic cavities, the radio lobes, which are filled with hot, magnetized plasma and cosmic rays. The particles in these lobes spiral around the embedded magnetic fields, emitting synchrotron radiation, which we detect as the faint radio glow that LOFAR saw. The sheer size of Alcyoneus's lobes poses a significant theoretical challenge. Jets lose energy as they propagate. They do work on the surrounding medium, pushing it aside. They spread out due to pressure differences. Eventually, they should run out of momentum and stall. Models of jet propagation based on known physics and the estimated density of the intergalactic medium suggested a maximum size for such lobes of a few million light-years. Alcyoneus is more than 5 times larger than that theoretical maximum. So, what's different? The leading explanation lies in Alcyoneus's environment. By mapping the distribution of galaxies in its vicinity, astronomers found that it resides in a region of space that is significantly underdense, a cosmic void or a very sparse filament of the cosmic web. The intergalactic medium in such regions is far less dense than average. Think of a jet trying to push through water versus pushing through a thin mist. In the mist, the void, there's far less resistance. The jet can maintain its collimation and momentum for a much greater distance, inflating lobes to unprecedented sizes before its energy is finally dissipated. Alcyoneus's host galaxy had the luck or the misfortune to turn on its jets in one of the emptiest neighborhoods in the observable universe, allowing its outburst to expand almost freely. Other factors may contribute. The jet activity might be unusually long-lived or episodic, pumping energy into the lobes over a longer period. The magnetic fields within the lobes might be particularly well-ordered and strong, helping to contain the plasma and prevent it from dissipating too quickly. The central black hole's spin might be exceptionally high, providing more rotational energy to power the jets. But the sparse environment is considered the primary enabler of its record-breaking size. Alcyoneus is not just a static monument, it is a dynamic event. The energy contained within those lobes is almost beyond comprehension. It represents the converted gravitational energy of countless suns' worth of material falling into the central black hole, channeled into intergalactic space. This energy input has a profound effect on the galaxy's surroundings, a process known as feedback. The hot lobes heat the sparse gas in the void, preventing it from ever cooling and collapsing to form new galaxies or stars. Alcyoneus has effectively sterilized a region of space 16 million light-years across, suppressing cosmic structure formation on a grand scale. It is a dramatic example of how a single, relatively small black hole can influence an environment billions of times larger than itself. What is the fate of Alcyoneus? It is ephemeral on cosmic timescales. The jet activity that powers the lobes will not last forever. The fuel supply to the black hole will eventually be exhausted or cut off. The jets will shut down. Without fresh energy injection, the radio lobes will no longer glow brightly in synchrotron radiation. The hot plasma will slowly mix with the surrounding intergalactic medium through turbulence and diffusion. The magnetic fields will decay. Within a few tens of millions of years, a blink in cosmic time, the magnificent structure will fade from view, leaving behind only a slight entropy increase in a vast cosmic void. The host galaxy will return to appearing ordinary, its brief reign as the largest known structure, a forgotten episode in the deep past. The discovery of Alcyoneus and the study of IC 1101 force us to confront fundamental questions about limits. Is there a maximum possible size for a galaxy, for a radio structure? The answer is nuanced and depends on which physical processes are dominant. For galaxy growth via mergers, the IC 1101 path, the limits are set by the cosmic environment and time. A galaxy can only grow as large as the reservoir of matter available within its gravitational reach. In the center of the richest clusters, that reservoir is enormous, allowing for monsters like IC 1101. However, dark energy's accelerating expansion is now pulling potential material beyond the gravitational horizon of clusters. We may be living in the epoch where the largest galaxies of all time are reaching their final form. There may be no fundamental physical law prohibiting a larger galaxy than IC 1101, but the practical conditions to create one may no longer exist in the evolving universe. For radio lobes, the Alcyone path, the limits are set by jet power, duration, and environmental resistance. Theoretically, in an almost perfect vacuum, a jet could propagate almost indefinitely until the expansion of the universe itself stretched it apart. But perfect vacuums don't exist. There is always some resistance. The discovery of Alcyone shows that our estimates of that resistance, or the efficiency of jet propagation, were off. Its existence suggests that in the most optimal environments, extremely underdense voids with long-lived jet activity, structures even larger than Alcyone might be possible. Future telescopes like the Square Kilometre Array (SKA) will scan the skies with even greater sensitivity, and they may well find radio galaxies that make Alcyone look modest. Beyond these specific giants, the cosmos is structured on even grander scales. Galaxies are not scattered randomly. They are arranged in a vast cosmic web of filaments, walls, and clusters, surrounding enormous voids hundreds of millions of light-years across. This web is the largest pattern in nature, the imprint of quantum fluctuations from the universe's first instant, stretched to astronomical scales by inflation and sculpted by gravity over 13.8 billion years. Compared to these filamentary structures, even Alcyone is a local phenomenon. The Sloan Great Wall, a filament of galaxies over 1.3 billion light-years long, makes our galactic titans seem like mere threads in a tapestry of inconceivable breadth. This brings us to the ultimate limit, the horizon of the observable universe itself. We can only see objects whose light has had time to reach us since the Big Bang. That horizon is currently about 46.5 billion light-years in every direction, defining a spherical volume containing all that we can ever know. No galaxy, no structure of any kind can be larger than this observable sphere. And within that sphere, the cosmic web defines the upper limit of coherent, gravitationally bound structure. We are, in a very real sense, living inside the largest structure we can possibly comprehend. The observable universe itself, with its intricate web of matter and its haunting, accelerating emptiness. The contemplation of these scales is more than an intellectual exercise. It is a transformative experience. It changes our perspective on our own existence. Every human life, with all its complexity, passion, and pain, is played out on a microscopic stage in a forgotten corner of a galaxy that is itself a nondescript speck in a universe of giants. This can feel crushing, inducing what philosophers and psychologists have termed cosmic vertigo, or the overview effect on a conceptual scale. Yet, there is a profound beauty and even a strange comfort in this insignificance. All our earthly conflicts, our anxieties, our struggles for power and recognition are utterly meaningless on the cosmic stage. The universe is utterly indifferent to them. This realization can be liberating. It invites us to focus on what truly matters: connection, understanding, beauty, and the shared, fragile experience of consciousness on this pale blue dot. Furthermore, our ability to comprehend this scale, to build the instruments and the mathematics to measure it, is a triumph. In a universe of pure physics, matter has organized itself into beings that can look back and understand the processes that created them. We are stardust become conscious, the universe gazing at itself through our eyes. The discovery of IC 1101 and Alcyone is a milestone in that self-awareness. It shows us the outer boundaries of the cosmic arena in which our story is set. As our technology advances, we will undoubtedly discover more giants, pushing the boundaries of the known further out. Perhaps we will find galaxies that have merged entire clusters, or radio lobes that span hundreds of millions of light-years in the emptiest voids. Each discovery will humble us anew and expand our understanding of the laws of physics under the most extreme conditions. For now, we sit in the quiet of our medium-sized galaxy, under a sky that is but a tiny window onto infinity. The light from Alcyonius has been traveling for 3 billion years to tell us its story. The light from IC 1101 for over a billion. They are messages from the deep past, showing us what the universe can do. They are reminders that we are part of something vast, ancient, and unimaginably grand. Our time here is brief, our world is small, but our minds can embrace the cosmos. In that act of understanding, we find a meaning that transcends our physical scale. We are the universe's way of knowing itself, and the journey of discovery has just begun. So let us continue to look up and out with wonder and humility. Let us continue to build better eyes to see further and sharper minds to understand deeper. The night sky is not a ceiling. It is a doorway, and the giants beyond are beckoning us to explore the infinite possibilities of existence. The story of the biggest galaxies ever discovered is not ending with this telling. It is an ongoing narrative written in the light of countless stars, and we are privileged to be its readers, its interpreters, and its humble witnesses. And with that, we leave you to your own contemplation of the cosmos. May the vastness above inspire not fear, but a quiet awe. May the knowledge of our smallness bring not despair, but a profound appreciation for the precious, fleeting, and beautiful experience of being alive and aware in such a magnificent universe. Good night.